All right, the next function we are going to look at is x squared minus 2x plus 4 over x minus 2. Again, when you're doing these problems in your homework, I think it tells you exactly what all the pieces to find, so you don't have to like remember all of these. But the first thing we're going to do is find the x-intercepts. Okay, we find x-intercepts by plugging in 0 for y. So 0 equals x squared minus 2x plus 4 over x minus 2. So yeah, we multiply both sides by the denominator. Of course, that's going to cancel. Those cancel, and that one's just 0. Now, I don't think this factors, and also if you do the quadratic formula, you're going to find that there are no solutions to it. So there are no x-intercepts to that. And you can do all the work through, but that's what happens there. All right, next we're going to look at y-intercepts. We find y-intercepts by plugging in 0 for x. And I believe we will get -2. Sounds right. Okay, so I'm going to start this graph over here. And all we know so far is that we have a y-intercept at -2. Okay, let's see. The domain of this function is going to be all real numbers except can't have 2. And the reason we can't have 2 is we have a vertical asymptote there. Now, before I go graph that, let's talk about the horizontal asymptote. Going back up here, the degree on top is bigger than the degree on bottom, so there's actually no horizontal asymptote. But the degree on top is 1 more than the degree on bottom, which means we have a slant asymptote. Remember, to find slant asymptotes, we are going to use long division. So x squared minus 2x plus 4 divided by x minus 2. So we need an x on top. It's going to be x squared minus 2x. Draw the line, change the signs. Those both cancel, and here's our remainder. Now remember, when we're talking about asymptotes, we get to ignore the remainder because as x approaches infinity or negative infinity, this is just basically going to be 0. So our slant asymptote is y equals x. So let's put those asymptotes on the graph. We said we had a vertical asymptote at 2, and we have a slant asymptote at y equals x. So this is taking shape nicely for us. What else can we find out about this? We can look at the limits. Remember, the limits are what we did in the last lesson. So I'm not going to walk all the way through that process, but as x approaches infinity, it is approaching infinity, and as it approaches negative infinity, it is negative infinity. So end behavior is unbounded. Oh, and symmetry, that's what else we can check for. So to check for symmetry, we're plugging in -x, so the original function's up there somewhere. So negative x squared minus 2 times -x plus 4 over -x minus 2. That does not give us the exact same thing that we started with, nor does it give us the exact opposite. So we don't have any particular symmetry on this. Okay, I think that's everything that we can find out from the original function. So now it's time to look at the derivatives and see what we can do. So remember, the original function is x squared minus 2x plus 4 over x minus 2. And we're going to take the derivative of this. So we have a quotient rule. So low d high is going to be 2x minus 2 minus high d low is just 1 over the square of what's below. All right, nothing to factor out of this one, so we're just going to FOIL and combine like terms. So 2x squared minus 2x minus 4x plus 4. Going to distribute that negative. right, so I get x squared minus 4x. Just that, I believe. Sure. I'm going to go ahead and go one more step and factor out the x. All right, so there's my first derivative. So my critical numbers, that is anywhere where it is equal to 0, so it's going to be 0 and 4. And also anywhere where the derivative is undefined, of course, which is at 2. Now, that's an asymptote, so it's not going to be a minimum or maximum, but we still need to consider it. And we're going to put these on the number line. And we're going to plug into the first derivative. So 0, 2, and 4. We're plugging into this to see what kind of numbers we get. If we plug in a -1, we get positive. If we plug in 1, we get a negative. If we plug in 3, we get negative. And if we plug in 4, we get positive. Okay, so remember, this is an asymptote. But here at 0, we go from increasing to decreasing. So we have a relative max at 0. Go back to the original function, 0, -2. That's how we find that y value. And then it goes from decreasing to increasing at 4. So we have a relative minimum at 4. And you just have to go back into the original function to plug in. I think it's 6. Okay, so back up to our graph. 0, -2 is a relative maximum. Okay, so that means it's coming up and going back down here. And then the point 4, 6 is a relative minimum. So it's coming down and going back up there. And we have a really good idea of what this is going to look like just from that. The last piece is to check out the concavity of it. So we got some space here. I think this will work. So the derivative is, I'm going to go back to the x squared minus 4x version of this. Okay. We're going to find the second derivative so we can determine concavity. So we have low d high, which is going to be 2x minus 4, minus high d low is going to be 2x minus 2 over the square of what's below. All right, again, just like the last one, I think we should factor out an x minus 2. So that's going to leave us with x minus 2, 2x minus 4, minus 2, x squared minus 4x. Sorry, I can't see that. My paper is starting to shift. It's kind of annoying. All over x minus 2 to the 4th. One of those cancel. And then we're going to FOIL and combine our like terms. So let's see what happens here. So 2x squared minus 4x plus 8 minus 2x squared plus 8x. So remember, that's just the numerator. Those cancel. Those are all going to cancel. So we end up with 8 over, paper's moving, x minus 2 cubed. That is our second derivative. Okay, when we set that equal to 0, the only thing we have is 2. Our only possible inflection point is 2. That's the only place that the second derivative actually is undefined. Now, remember, that's an asymptote, but we still need to put it on that number line. And then we're going to plug points in and see what happens. Turns out, remember, we're plugging into the second derivative. This turns out to be negative. This turns out to be positive. So on this side of the asymptote, it's concave down. On this side, it's concave up, which I believe is what we already have on our graph. So this is a fantastic graph of our original function.